Hello! So today we're going to go over two chapters, chapter 17 and chapter 18. They have very similar topics. It's just different ways of accessing that data. So first we're going to go over data mining in chapter 17. So we are going to learn how to understand and apply four data mining processes: data prep, exploratory data analysis, model development, interpretation of results. Then we're going to discuss the association rules mining algorithm in depth, and we're going to learn how to use that and apply it in R using the A-Rules package. So let's get started. Data mining is also called machine learning, which is similar but not totally the same. It uses algorithms to look at data and find patterns in it, which are often used to make business decisions or improve efficiency. There are four steps. Realize these steps are not always strictly linear. So step one, making sure the data is organized, the blanks are filled in, and accurate data is cleansed, and that all of your data is coded correctly and is usable. Step two, getting to know the data, using histograms or other tools, guiding the model choices, and just so that you can personally understand what your data is saying. Step three, choosing and developing a model. And then finally, step four is the interpretation of the results, which is just making sense out of what the data mining algorithm has produced and given to you. Association rules algorithm, again, sometimes called affinity analysis or market basket analysis. It looks at pairings that occur, such as items purchased together at a grocery store. This is the example we're going to go through. For example, and I love this comparison, and it came out of the book, so I can't even take credit for this, but if diapers are purchased, then beer is also purchased. That is the best example in the world, especially if you have children. If not, you will someday maybe. Anyway, the algorithm is going to evaluate these associations for two things. Number one, support. Number two, confidence. Support is the proportion of times that a particular pairing occurs across all of the shopping carts. Confidence, on the other hand, is how frequently a specific pair occurs among all of the times that you have at least one of those items present. So there is a difference between support and confidence. New library alert. We need to install and activate a new library called A-Rules. And from that, we can actually start with a built-in data set called groceries. So the first thing we're going to do is we're going to create that data set using groceries. Okay, so now let's run a summary of that and let's see what's in there. We can see here that groceries is an item matrix right there, object, which means it's going to be arranged in rows and columns. Okay, over here we see that it is in sparse format. That means that very few of the items exist in any given grocery basket. So here we can see an item is going to be represented as a 0 if it's not in any basket, and by a 1 if it is. This is how you can see that it's going to be sparse, because most of the baskets are not going to have every single item, so you're going to have a lot of zeros in there. You can also look down here and see a bunch of the items that are looped together. You can also see the most frequent items at the top. We can also use something called an item frequency plot here with our data called groceries. This is going to show the relative frequency with which each of the items are going to occur in the matrix. Now, we were able here to specify that we want to plot items only that have a minimum level of support over 1. Remember, support is that relative frequency of occurrence of something. We can see, though, that some items are missing from this plot. Okay, we can play with the levels of support and confidence and see what changes. So we played with some of the support and confidence levels here. We also have a new parameter here called CEX names. This is going to rotate those names so that they're not going to overlap and become unreadable. For this example, we used a support of 0.05 and a names of 0.5. See how we've increased this from the very few number of items that we had in the previous histogram to about 25. Now, one thing we notice is that item frequency plot does not take a data frame, okay? It actually takes a transition data set. They're completely different. But if we have a data frame, we can convert it to the transition data set. At this time, we're going to use another built-in frame called adult UCI. You can always do a summary, but it's just know that it's a data frame for this example. The first thing you're going to need to do is to convert any numbers or strings into factors. Okay, for each column, we're going to use this as factor method and send it the column. So we're just replacing the columns with the column as a factor. One thing to note is if your column name has a hyphen in it, like this one, and this one, and that one, like these four right here, you need to add the single quotes around those column names. The reason why we do that is that if we don't have the quotes around the column names, it's going to think you're going to try to like subtract something, and it's going to give you an error. We're not subtracting anything. It's actually part of the name. Okay. After all of this cleaning, we're finally going to convert it into a data frame by using this as command. The final command here is going to generate the item frequency plot. So let's take a quick look at this plot. Here we go. So now we know a little more about this data set. So using this data set, let's look at how we can generate some rules using the APRIOR, that one command. I don't know how to say it. I don't know if you can say it. I've never had to say it before. I just know it's like this command. Anyway, this command is going to scan the data set for any rules, okay, in your transaction data. It iterates through using what it calls a level-wise search. So the first level is single items: milk, bread, tea, eggs, fish. It's one item sets. The second level is going to have two item sets: milk, tea, bread, fish. Okay, you can see how we're increasing. So in order to make it to a two-item set, it has to have sufficient support in each of their subsets in order to be included. Okay, your algorithm is going to keep leveling up here until there's nothing left to level up. Okay, as you can see here, from here we drop the ones that don't have sufficient support as we move on to the next level. So you can see from here we dropped eggs because there was only one. Okay, then we take our new subset has only the four that had sufficient evidence. Now this actually goes down below it. So we say milk and bread, milk and tea, milk and fish. Okay, bread, tea, bread, fish, and tea, fish. Okay, so we make the second level by pairing up each of the singles that passed the first test. From this, we can see how many are in each of these. We can see we have two of them with ones, those get dropped. Okay, so you can see how we're building on this. Only one 3-item set has enough for support, which is the bread, tea, fish, okay, to be included. With each level, the items that don't have enough are just completely dropped out of the algorithm and it moves on. So you can see how it kind of hones in on the one rule that it's looking for. The rules are formatted as if left-hand side, then right-hand side. Okay, so for each instance of a thing, the left-hand side, the thing on the right-hand side will occur a percentage of the time. Support for a rule refers to the frequency of occurrences of both members of the pair. Right-hand side usually contains one item, while left-hand side can contain, say, more than one. We can set values for the support and confidence minimums that we talked about before. If we store these rules into a variable called rule set, we can actually look at them using our summary. So if we set summary here, we actually have a set of 15 rules. Okay, we've got some great information, we've got some minimums, and we've got some basic statistics on the support and the confidence, which we know what they are, but now we have a new one called lift. Lift is an attempt to quantify how interesting or how novel that rule is going to be. Lift is going to take into account the support for a rule, but also gives more weight to the rule where the left-hand side and the right-hand side occur less frequently. The larger the lift, the more interesting the rule may be. Interesting, depends on what you define interesting as, right? You can look at all of your rules and how they match up with their support, confidence, and lift if you use inspect. Okay, so it's got left-hand side, right-hand side, support, confidence, and lift for each individual rule. Now, what might be a little bit more helpful is to actually visualize these rules. So, new library alert, you can use the A rules VIZ to visualize. So it's the same A rules as before, but we have VIZ after it for visualization. Now you can plot the confidence versus support with the lift being the gradient of the color. So your lift is going to be, remember, that is how interesting your rule is. The A rules visualization captures novel combinations that didn't have enough support or confidence to appear in any of the previous plots, so it kind of makes it a little bit more interesting. That's really all there is to association rules mining algorithm. Pretty easy applications here, but let's take a look at the next chapter, chapter 18, and we're going to look at some vectors. So chapter 18 deals primarily with the support vector machine, or the SVM. So what we're going to do is we're going to explain the difference between supervised and unsupervised learning. We're going to use the SVM technique, and we're going to create a training data set versus a test data set environment in R, and we're going to see how to actually implement an SVM. First though, let's take a look at what supervised and unsupervised learning. So supervised and unsupervised learning are two types of data mining approaches. Unsupervised learning, no particular criterion is a goal. You're just simply looking at the patterns that emerge organically, kind of like what we just did in chapter 17. Supervised learning, on the other hand, is going to train an algorithm on established data and then test it on a set of new data. If your algorithm is well built and trained correctly, you will get the correct result. So you can see the difference between the unsupervised and the supervised. Now we can look at SVM to classify emails into whether it is a spam email or not a spam email. So this is the example we're going to use. So what you want to look at is you want to look at separating your data into two buckets. Okay, so here we've got say spam emails and non-spam emails. Let's look at the light blue dots as spam and the dark blue dots as not spam. Now keep in mind this one right here in figure 18, that's pretty clean, right? So most of the time our data sets are often going to be messy, but we're going to kind of look at it as clean for right now. Your SVM is going to create what's called a hyperplane, okay, and that's kind of represented by these lines here in these two figures. You can see a very clean divide here. It's a very straight line here. Not so much, a little bit messier, right? This is going to separate your data set into planes, okay? This is all two-dimensional, but let's take a look at a 3D model of it, okay? An SVM is going to map a low-dimensional problem into a higher dimensional space to describe geometric boundaries between regions. The result of this analysis is going to be your mathematical description of the position and orientation of that hyperplane or that separation or planar separation. Any new data that you're going to introduce into this is going to be mapped into the 3D map, and those coordinates are going to return what the anticipated results of that new data are. Does it belong in bucket A or does it belong in bucket B? Okay, so that's really what we're looking at. Again, new library alert. We're going to be using a new library called KernelLab. There is an existing data set of spam emails in there called spam. That's what we're going to look at. We can see the dimensions of the data structure with a dim command. Now this output is going to be rows and columns, and we can also see what is in a specific column with the table command down here. Okay. Type in our table of data is going to be the criteria variable that's going to indicate whether the spam is classified as spam by humans. Okay. So it's going to have either spam or non-spam, and this was by human experts. And so what we're going to do is we're going to create an algorithm to attempt to duplicate the human experts. We're going to use this table function because type is a factor rather than a numeric variable. Okay. Then finally, we can use the data from the table command to divide this data into data sets. So remember, what we want to do, because these are learning, we want to train the algorithm to have that hyperplane or that planar view. From that, we want to be able to take outlier data or outside data and put that in there and see if it was interpreted correctly. So what we need to do is we need to divide our full set of data up into training data and test set data. It's important to randomize your selection of cases for the training and test set data to make sure you don't have any bias, and to make sure they both have outliers and they both have, pretty constant values. The data sets may be stored in some wonky way, so randomizing actually prevents you from doing that, from creating a bias that you don't even know. It may be saved alphabetically and you don't know it, okay? So the easiest way to make sure there is no bias is by randomizing. This example is creating a randomized index of sample, okay, from your spam. Okay, so here we've got a total of 4,601 elements and they're random. Okay, now we have to take that random data that we randomized and we're going to have to create a cut. So let's do a 2/3, 1/3. Let's do a training on 2/3 and let's save that last third set of data for the test. So first we calculate a cut point of 2/3 based on the row numbers, okay? And we're going to build the training set. The training set is going to go from 1 to that cut point of 2/3. Then we're going to create a second set of test data from the 2/3 point to the end, okay? Remember, SVM is going to train to find that hyperplane location, so we have to train it and then test what we have found. Okay, first we're going to generate the model from the training set of data, okay? We use the KSVM command with some parameters. Let's take a little look at some of these parameters. So here the data is the training set. That's pretty much self-explanatory. Kernel equals RBFDOT, okay? That's the radial basis function kernel. That's going to take the set of inputs from each row and calculate a distance value based on the combination of the many variables in the row. The algorithm is going to adjust the weighting to get the maximum separation of distance between the spam and the no spam. The next variable we have here is kpar, and we have it set to automatic. That is going to refer to a variety of parameters that can be used to control the operation of the kernel. Okay, and the kernel here is an RBF kernel. Next, we have an argument that says C equals 5. The C argument is going to be the so-called cost of constraints. A small value for C is going to give a large margin of separation, but you have the possibility of having many more mistakes. A large C value can result in more accuracy, but a smaller margin of separation, meaning the model is going to be less generalizable because it's trying to be incredibly precise. So you need to decide what is your trade-off, right? You can have large margin of separation or accuracy. Cross equals 3 here. This is going to refer to the cross-validation model that the algorithm uses. So this model is using a threefold cross-validation to generate the probabilities determining whether it is spam or not spam. That's a lot of stuff going on there. You can look at the output structure by just using the SVM output command, okay? It gives a little bit of information, but not a whole lot. Things to note from this output, though, are your sigma parameters, okay, and the large number of support vectors, okay. The training error rate here of 0.28 or 0.29, 2.9, very, very low, okay. So the training error rate is very low. What does give a better set of data, though, is, doing a histogram of the alpha of it. The alpha accessor reveals the values of the support vectors. Okay, the maximum value of the support vector is equal to the cost parameter discussed earlier. If we adjust the cost parameter, we get fewer problem points near that vector, but we increase our error. So let's change that C that we had from a 5 to a 50. And let's look at another histogram of the support vectors and let's see how that affects our data. Here we go. We've changed C to equal 50. Our sigma is still at, 3%. That's still good, right? The number of cases where the support vector is at the maxed out value is down to about 100. Here's my maxed out, right? The cases with a support vector value near 0 these are the easiest cases to classify. So those are the ones that are the furthest away from that hyperplane cut. These cases that are on the wrong side of that hyperplane are even very far away from the hyperplane. Those are usually your outliers that you kind of want to take a nice hard look at and see what's going on with them. So let's investigate those 0 support, and then we're going to investigate the ones on the other side. So let's look at those outliers. Let's find the index number of a few of those support vectors that are going to lie near the 0 or very close to the hyperplane. Okay, this right here is going to give, these are index numbers, remember. So once you have the output of index number, you can actually look at a specific data set or row from these indice numbers. So let's take the first one at 90. And say train data, I want to see row 90. This is going to give you all the information that is in row 90. Now the biggest thing that we're looking at over here is the type, which is the last one. Remember, this is how a human has classified this email, as a non-spam. It's easy to see here we've got a whole bunch of zeros going on, so it's very easy why, these are our indicators of that it might be spam. We have all zeros. It's very easy to categorize this as non-spam. Now, let's look at those outliers and those hard cases that were over on the right of our histogram. We can use something called alpha index, and we get a list of the 92 indices where the support vector was maxed out, okay? We're going to pick row 11. I don't have the output here of the data. Not sure why I didn't do that. That's okay. We're going to pick row 11. This record is not going to have any suspicious words, but it does have a wonky, long string of capital letters. So it is a non-spam. You can look at a few of these outliers and try to see if you can tell why they were so difficult to classify. We can also use these support vectors to predict the outcome in our test data. This is where this test data is coming in. This is where our good planning ahead of time is really going to pay off. So we can use the command predict. But this time, remember, we're going to send it the test data. Remember, we had train data versus test data. We're going to send it test data. And we are going to do the SVM output, which is what we learned from the training data. Here we can then make a data frame out of what was given. Now what's given here is called a confusion matrix. Okay, what it's telling us is this is basically testing your data. Here we want column 58, which is the column number that is the human specified whether it was spam or non-spam. And then what we're doing is we are going to take out the column in the votes data structure SVM pred here, so that your zeros are going to be non-spam and your ones are going to be spam. Okay, so what we're doing is we're comparing what the human classified it as here on the rows, and the columns are going to be how the algorithm classified it. Finally, if you go ahead and do the table command, you can see your table. Okay, remember this is called a confusion matrix. This is basically where it very well shows how your algorithm didn't work, okay? So you can see from here we've got 38 cases that were classified as spam by the algorithm that were classified as non-spam by the human, okay? Here again, we look at this main diagonal. These are the errors, okay? We had 68 that were spam classified by humans that were considered non-spam, that were considered non-spam by the algorithm, okay? Now the counter diagonal, these are the correct, okay? So we had 854 non-spam classified correctly and 574 classified as spam correctly. Overall, you can see that this SVM worked actually pretty well, okay? We have very low number of cases where the errors were. That's all there is to your SVM. It is being able to predict where a data point will fall if you have your data divided into two buckets or two groupings. That's all there is from me. Thank you for listening. As always, if there are any questions, I am reachable by email or during office hours or schedule an appointment. And happy coding on your assignments.